Hello and welcome. So we have a couple of true-false statements here. So first off, for all these, it's kind of a typo on my version. It'll be fixed on yours. But we essentially have if A is a square matrix, important to note there, with all zeros along a diagonal, then A does not have an inverse. Now keep in mind, in order for something to have an inverse or not for any square matrix, the determinant of the matrix, whatever that matrix may be, cannot equal 0 if it has an inverse. Okay? If there is no inverse, then that means that the determinant does equal 0. Okay? So you want to make sure that you have a non-zero determinant if you want the inverse to exist. If there is a determinant of 0, your inverse won't exist. So looking at this one, if we have a square matrix with zeros along the diagonal, so let's just make up an example, right? So any diagonal has a 0, okay? And then we have numbers for the other things. If we try to take the determinant of this, we get 0 times 0, which is 0, minus the other diagonal, which is a times b. Now, unless you have a and b also being 0, or one of them being 0, then that means that it would be 0 as a determinant. But if a and b are non-zero, that means negative ab, right? That number would not be 0 and the inverse will exist. So if it has all zeros along the diagonal, then it does not have an inverse. That is false. Okay? So that doesn't, of course, not every matrix will be this case, right? If a happened to be 0 as well, then yeah, there would not be an inverse for this matrix. Okay? But that doesn't mean that every matrix will be non-invertible that way. Okay, the next one is if you have a row of zeros, then A does have an inverse. This is also false. Think about it this way. If you have a row of zeros, all right, numbers right there and there. If you try to take the determinant of this matrix, A times 0, that's 0, minus b times 0, also 0, we get 0, and that means that it is not invertible. There is no inverse for your matrix, and then you would be out of luck, right? So saying it does have an inverse, that's a false statement. If you have a square matrix with a column of zeros, then A does not have an inverse. This is a true statement, right? Think about it this way. If you have two numbers, right, and then you have zeros in the other column, then if you multiply these together, your first diagonal is 0 when you multiply them, minus the other diagonal, 0 times b, also 0. Okay, that means you have 0 equals your determinant. The determinant is 0, meaning the inverse does not exist, and column of zeros means that you're always going to have this case. Okay, and then if you have a non-square matrix, it does not have an inverse, also true. Because for non-square matrices, is essentially meaning that the determinant cannot be taken of a non-square matrix. So if you have, let's say, like a 2 by 3, so if we fill this with just random numbers, right, a, b, c, d, e, f, okay, we cannot take the determinant of a matrix like this. You can only take determinants of square matrices, meaning that if it's a 2 by 2, or a 3 by 3, or a 4 by 4, those are square matrices because the number of rows matches the number of columns. But if it's not square, there is no determinant because you can't take the determinant, and thus there is no inverse for those particular matrices. And then next we have every 2 by 2 matrix may or may not have an inverse. That is also true. Okay? Because when you think about it, if you have a 2 by 2 matrix, right, if I just start picking random numbers, no matter what numbers we pick, right, maybe our A times B minus C times D. If that number equals 0, there's no inverse. But if it doesn't equal 0, right, if it doesn't equal 0, then there is an inverse. And so the may or may not makes this a true statement, where any 2 by 2 matrix may be invertible or it may not. Depends on what the numbers does, right? That's a case-by-case thing. Okay, so that is all of your true-false statements. Really, it just plays with determinants. So just make sure you're reading these very, very carefully. All right, if you can come up with one counterexample that makes it false, it is false. Okay, all right, thanks so much for watching.